vapor pressure, and the Clausius-Clapeyron equation. If we have a liquid and apply some heat to it, the temperature of that liquid will rise. This is because the energy of the molecules of that substance are increasing, and their average kinetic energy has increased. Some of these molecules will have enough energy to break free from the intermolecular bonds and escape as a gas. This can also happen in a solid, but the number of molecules that escape is almost negligible. At temperatures above absolute freezing, some portion of molecules will be able to obtain enough energy to reach escape velocity, even at temperatures where that substance would not generally be in the gas phase. The higher the temperature, the more chance molecules will gain enough energy to escape into the gas phase. If we seal a liquid inside of a container, some of the molecules inside will reach escape velocity and become a gas. This gas will increase the pressure inside the container. As these molecules bounce around, there's a chance they will impact the liquid and be seated back into a liquid state by the intermolecular forces. The pressure exerted by the vapor in equilibrium with the liquid in a closed container at a given temperature is called the liquid's vapor pressure. It should not come as a surprise that the vapor pressure of a liquid is inversely related to the intermolecular forces acting on the molecules that make up the substance. Because intermolecular forces are connected to vapor pressure and influenced by the temperature and pressure of the system, scientists were able to derive an equation that uses these parameters to predict changes in vapor pressure within a system as these variables are changed. This equation is the Clausius-Clapeyron equation. This equation shows the quantitative relationship between vapor pressure and temperature. Delta H is the enthalpy of vaporization. R is the gas constant. A is a constant that is different for each substance, and T is the temperature in Kelvin. To make this equation easier to work with, we can do some mathematical manipulation and come up with this version. Because the natural log of A is constant for identical substances, we can compare changes in temperature and its effect on the vapor pressure of a single system by setting the initial value and final values equal to the natural log of A. And then to each other. This only works if we are changing a single system between different temperature and pressure states. Some more math and we get our final equation. Things to keep in mind when using this equation. Number one, the gas constant, as we have seen, can be different values based on the units. In this case, we need to use joules since we are dealing with energy values. This means that the enthalpy of vaporization must be in joules as well. Watch out for those values being reported in kilojoules and convert when necessary. The pressure values divide each other out, so the units can be anything if they are the same as each other. Finally, all temperatures in this equation need to be in Kelvin. Because we get Kelvin from Celsius by addition, it needs to be done before we start plugging it into any equations. Let's take a look at a problem and use the Clausius-Clapeyron equation to solve it. Suppose the atmospheric pressure inside a pressure cooker is 2.5 atmospheres. What would the boiling temperature of water be? We know that at 1 atmosphere of pressure, water will boil at 100 degrees Celsius. This gives us a starting condition. The heat of vaporization for water is 40.7 kilojoules per mole. Both our pressure values have the same unit, so we can use those as they are. 100 degrees Celsius needs to be converted to Kelvin, which is 373 Kelvin. We also need to convert 40.7 kilojoules per mole into joules to match the units of the gas constant R. This works out to 40,700 joules per mole. Now, we can plug in what we know and solve for the new temperature of the boiling water inside the pressure cooker. We get 401 Kelvin. work through pages 27 and 28 in the workbook. Intermolecular forces and solution formation. At this point, we should be comfortable with how to represent ionic compounds that have been dissociated in water. We have worked with these systems using complete and net ionic equations. Let's review and expand our vocabulary for the formation of solutions. A solution is a homogeneous mixture of two or more pure substances. We call the most abundant substance the solvent. This is the substance that the less abundant substance is dissolved into. We call that less abundant substance the solute. So solutes are dissolved into solvents. The solubility of a solute is how much of it can be dissolved into a specific amount of solvent. This number is different for every solute-solvent combination and is temperature and pressure dependent. Saturation is what happens when you add the exact amount of solute to reach its solubility point. Past this amount, no more of the solute will dissolve in the solvent. Supersaturation is when you add even more solute beyond the saturation point. This will create a precipitate because the amount of solute will form a solid until the amount dissolved is equal to the saturation point. It is possible to make a solution using any two of the phases we have discussed already, solid, liquid, or gas. We can dissolve gases into liquids like CO2 into soda, as well as solids into liquids, as with the ionic compounds we have looked at in previous classes. We can also dissolve one liquid into another. The ability of these solutes to be dissolved is affected by the intermolecular forces. There are some things we need to know about solution formation. Things tend to become more disordered. This is known as entropy, which we will discuss later. However, it is easy to see how the molecules in a solid are less structured once dissolved into a liquid. Like dissolves like. This is an important concept in chemistry. Polar molecules can form dipole-dipole interactions with other polar molecules, and dispersion forces work best when there are a lot of them. So polar things dissolve polar things, and nonpolar things dissolve nonpolar things. As we have seen before, the process of dissolving a solute requires breaking the bonds between solute molecules and surrounding them with solvent molecules. Both temperature and pressure affect the solubility of a solute in a particular solvent. We can see that the solubility of gases tends to decrease with increasing temperature, and the solubility of solids increases with increasing temperature. Let's take a close look at the process of solvation. In order for a solute to dissolve, the intermolecular bonds between molecules of that solute must be broken. This is an endothermic process. It requires the input of energy. Now, the intermolecular bonds between solvent molecules must also be broken up to make room for the new solute molecules. This is also endothermic. Finally, the solvent and the solute must establish new intermolecular bonds between each other for the solute to stay dissolved. This is an exothermic process. The total energy needed for the creation of a solution is the sum of all of these enthalpies. Let's take a look at an example of how we can keep track of these changes in energy in intermolecular bonds. Consider the molecule difluoromethane and propanol. First, consider what intermolecular forces exist between the molecules of each substance. Difluoromethane is polar, with this dipole moment, so it has dipole-dipole interactions and some London dispersion forces. Propanol is also polar, but it can also participate in hydrogen bonding and dispersion forces. Because these molecules are polar, they will likely form a solution. The above-mentioned intermolecular forces will have to be broken and new ones formed between solute and solvent. Between the solute and solvent, we have dispersion forces and dipole-dipole intermolecular forces. Thus, it will take more energy to break up the solvent than we will get back by forming the bonds. From this, we can predict that these molecules will create an endothermic solution. That is, it will take more energy to make them than we get back. We need to consider another type of intermolecular force. That is ion-dipole interactions. These are important in how ionic compounds dissolve into aqueous solutions. We know that water is polar, and that polar molecules have dipoles, which manifest as tiny charges on different ends of the structure. Thus, ions can interact with these dipoles based on their charges. Potassium sulfate dissolves into water, creating 2 positively charged potassium ions and 1 negatively charged sulfate ion. The dipoles of water will form up around these charges. This is why many salts are soluble in water. Work through pages 32 through 34 in your workbook. In our next chapter, we will consider kinetic. In our next chapter, we will consider the